is good for. It's its purpose in life. You have to use it or it'll be sad. Okay, so what we're going to talk about next is how to find limits. And for now, it's going to be just estimation and pictures and stuff. So this notation is read the limit of f of x as x approaches a is L, which means as the x's get close to a, f of x, which is the y, does that make sense? Gets close to L. So that's what that means. As your x's go close to a, your y's go close to L. So as you zoom in on that value of x, your y's are going to also get closer and closer to that value and sort of settle down and stay there. Okay, so that's what that means. And here's some pictures of it. So you could have something like this, where that's your a value. And as you get close to that, your function gets close to some L that is your y value. Okay, what if I do the same picture, but I put a hole there? Just pretend that I actually do the same picture, okay? Is the limit there still L? As the x's get close to a, but not all the way there, do the y's still appear to get close to L? Yeah. So you're approaching this little hole, but you're never going to get quite all the way there, and you're like, okay, I'm getting close to this L point, even though it might not actually exist there. What if I threw in a dot up there? Is the limit the same thing? It actually is. Okay, this is the weird thing. I know it seems weird. As you get close to L, do your y's appear, as you get close to A, do your y's appear to get close to L? All your view is you're just walking along and you're like, okay, I'm sinking down, I'm sinking down, I'm sinking down. You think that you're getting close to that value, right? Even though the function actually has some other weird value. But the question is, what are you getting close to when you're getting close to that particular y value? If the question said that value was like, I don't know, 10, and I said find f of a, that's 10. Like, what do you get when you plug in a? But the limit as x goes to a of f of x, that's still L. The fact that those two things are unequal means something about the graph. But the limit is the thing you're approaching. It's the value you get close to, even though you might not actually hit it. So one way to estimate limits is to make a table of values and to plug numbers in that are close to the thing that you care about. And how this will go in WebAssign is going to give you a list of numbers to plug in. Does that make sense? So this one, the numbers that we're plugging in are going to be close to, but not equal to 1. So I make a table of my x that I choose, and then the value of x minus 1 over x squared minus 1. Does it make sense that plugging in 1 is officially no good? Because you can't do 0 divided by 0, right? Okay. So first, let's plug in a number that's close to 1, but bigger than 1. So how about 1.1? So we do 1.1 minus 1 over 1.1 squared minus 1, and you get 0.526. Next number, 1.01. And you do 1.01 minus 1 over 1.01 squared minus 1, and you get 0.503. You can keep going picking smaller and smaller numbers, right? Now just to check, pick a number that is smaller, but instead of being bigger than 1, is a little bit less than 1. 0.9, yep. So I picked 0.9, and that would have been 0.9 minus 1 over 0.9 squared minus 1. And that gives you 0.476. And you can see where this is going, right? And that gives you 0.498. So when our guesses were a little bit bigger than 1, it turns out that we were picking things. What happened is that the values seem to be getting close to 0.5, a little bit bigger than 0.5, right? What happens as your values of x go up to 1? Close to 0.5, but from below, right? So what's your guess that this limit is equal to? This limit is 0.5. And there are ways to find it exactly, and that's what we're going to discuss in class next time. But for now, it's just pick values and guess. And WebAssign will either give you specific values, or it might ask you to just like make a table and guess your own. But then in that case, all you put in is the answer, not like the work. Okay? I'm going to skip 2 explicitly, other than to say one thing. Make sure that your calculator is in radians. Does that make sense? So when you plug in numbers, make sure your calculator is actually in radians. I'm not sure if it'll matter if it's in degrees, but just be careful. So pick some numbers that are bigger than 0, like 0.1, 0.001, etc. What were the numbers? What numbers would you choose that be less than 0?
Negative 0.01.
And negative point, yeah, stuff like that. Okay. Those would be the things that you pick, and then what do they get plugged into? Plugged into sine x over x. The guess is this will actually equal 1. So, and you'll get that if you plug in those values and just start calculating. Okay. So guessing sucks for lots of reasons. The first of which is like tedious, and the second of which is probably inaccurate, right? Does that make sense? Like these have been pretty easy to guess because things appear to be going to a specific number. But sometimes the manner in which you guess numbers can introduce something that sort of makes it appear that something's happening when it isn't. So this one, I thought I fixed this. Did I make your note sheet say pi over x?
Yes.
Yeah, and it's supposed to say pi over x. I fixed it in one place, but not the other. Okay, so let's do a couple. So x is going to 0. Let's pick x equal to 0.1, for example. So if I do pi divided by 0.1, that's the same thing as 10 pi. Does that make sense? Do you buy that?
Yeah.
Okay. What is sine of 10 pi?
0.
0, okay. If I pick 0.01, what is pi divided by 0.01? 100 pi. And what's that going to be?
0.
And you're always, does it make sense you're going to keep getting 0 every single dang time? Does that, you see that? 0.001, so is the limit going to 0? So as x goes to 0, does this function, there's this picture, does this function settle down and eventually do the y's appear to go to 0 here? Doesn't look like it, right? So if you zoom in on this function repeatedly, it gets like uber dense in the middle and it has all these oscillating lines that keep getting closer and closer and closer and closer together. Does that make sense? So this limit does not exist. And we guess wrong. Like I would be inclined to say, oh, well, the limit must be 0. But this function also appears to go up to 1, right? So that's the point, is that if you're making a guess, a good thing to also do maybe to look at a picture of it and see if your guess and your picture sort of show the same thing. And we'll look more at some pictures in just a second. But the problem with this limit is limits have to settle down. Yeah, go ahead.
So, but on test, we don't have a calculator, we can't look at pictures, so.
That's true, but I won't give you one that needs it. I'll give you the picture, right? But your homework is more about exploring and playing with these things, so in that case, look at a picture. Does that make sense? But for this stuff, no, on tests, you won't have a grapher to calculate your result, but you might be given a graph or something like that. So like what I could do is say, give you this picture and say, does the limit as x goes to 0 exist? And you're like, heck no, it doesn't settle down and decide to be one thing. Okay, so those are some of the pit guessing. Number one is it takes a long time. And number two is you could guess wrong, and that would be sad. It also isn't clear when you should stop guessing, right? Like how we kind of guessed that some limits were like 0.25, but how do we know it wasn't like 0.250005, right? Like how do we know exactly what it is? And so we kind of thought, oh, maybe it's this nice pretty number, but we're never quite sure. So we'll learn ways to be quite sure tomorrow. And the other thing I have to make you understand is just some notation. So this notation, notice how there's like a little superscript there on the A that's a plus sign. Have you seen that before? Maybe? Okay. If you have a grade, if you haven't, here's what it means. It means that x approaches A from the positive side. Sometimes that's called the right. So in your picture, if this is your A, you're coming at A from that direction. And the plus means the numbers are a little bit bigger than that A. Okay? And the other notation, A minus, is called the left-hand limit. That means x approaches A from the negative or the left side. And if you're coming at A from this side, the x's that you're choosing, or the numbers that you're looking at, are always a little bit less than A. And we kind of did that with our guesses, didn't we? I forced you to pick some numbers that were less than the number we were looking at, and some that were bigger. So that was the left and right side. And technically, to know if a limit exists, you've got to look at it from both sides and see, well, if I come at it from the left and I come at it from the right, do they go to the same spot? And that's what the next thing says, is that the limit is equal to L if and only if the left and right limits equal the same thing. So you come at it from below and from above and they go the same place, then the limit is that number. Here's an example of that not happening. Something like a piecewise function, if that's your A value. As you come at A from the left, you have that number. From the right, you have this number, and they don't match up, so the limit doesn't exist. But if they do match up, your limit does exist. So like for this kind of picture, if you come at it from the left and the right, are you approaching the same y value? Yes. Okay.
So this is still for the secant and tangent.
Yeah, doing limits will allow you to find secant and tangent lines. Yep. Okay, so just look at this picture and see if you can interpret what these limits are going to be. Okay, so as x goes to 2, what side is this first one from? From the left side. So you're on your picture and you're going at 2 from this side. What y value are you getting close to? 3. So that limit is 3. Okay, how about as you go to 2 from the other side? The y gets close to 1. So what about C? Limit as x goes to 2 with no side specified. Does not exist. And you must give your answer in WebAssign like that with all capital letters. And you can say as A is not equal to B. Okay, how about as you go to 5 from the left? What do the y's get close to as you go to 5? 2. How about from the right? Also 2. And so how about the plain old limit? That actually is still 2. Okay? The fact that there's a point filled in below there is that when you do limits, you don't actually get all the way to 5. You get close to 5. And so if your worldview is just getting close to but not to 5, you don't know about the point being like filled in below down there. So you say, okay, well, I appear to be getting close to 2. There just happens to be a sinkhole. And so if I add one more question, and I said find g of 5, what would that equal? 1. Because this means figure out what is the x value, the y value when you plug in 5, right? I know, yes, go ahead.
It's a little higher.
Hmm?
It's a little higher than 1. It's higher than 1.
Oh, it's a little higher than 1?
Slightly.
Ah, crap, 1.2.
Okay, you were kind of cheap your line there.
I was, yes. Okay, well, the point is it's not equal to 2, right? But yeah, about. Okay. Do you get the picture thing?
What's a note? You don't write any limit notation. You're just writing G of 5.
Yep. Like, what do you get when you plug in 5? And I think other people's like sort of their complaint is that, well, there's a hole there. Why is the limit exist? Like, what about this whole limit thing? But limits, when you get close to that number, what happens is you're near, not all the way there. This thing, this G of 5, is what happens when you're actually there.
Really just plugging in the value.
Mm-hmm, exactly. Whereas this one, you're not necessarily plugging in the value. Okay. Sketch a graph of this function and then use it to figure out when the limit exists. Okay, so 1 plus sine x if x is less than 0. So that's on which side of the y-axis, the left side or the right side? Left side. Okay, so this is 2 pi. There's negative 2 pi. It's a sine picture, which usually does, I'll just rub the dots of the picture. This, right? And then how's it been shifted? Up 1. And then there's an open circle when you cross the y-axis. So, etc. Let me erase my dots that don't need to be there. Okay. How about the cosine business? Where would cosine usually start? At 1. And then it would cross at pi halves and be down at negative 1 at 2 pi. What does this negative do to it, though? Flips it over the x. So it should be down there, that's filled in. Still crosses there, goes up. It's this kind of thing. And that's pi, that's where we stop. Should both of those dots have been filled in? Yeah, okay. I agree. We'll make it a patriotic curve. Okay, and then sine of x if x is bigger than pi. So sine usually would have begun at 0, gone up, down, down, up. And we don't use all those dots, do we? Which dots do we use? From pi on. And at pi, would I have an open circle or a filled in circle? Open. And then it would, continue. Okay. So where does this limit not exist? At what values? At a equals, and pi. But everywhere else is okay. Does that make sense? Okay, so if I wanted to give the places where the limit exists, the best way is to give it as an interval. So does the limit exist everywhere up until 0? Yes, okay, so that would be negative infinity to 0. You don't include 0 on either side because the limit doesn't exist at 0. Even though 0 is filled in on this side, you don't include that. And you're all good from 0 to pi. And then from pi to infinity. That's an interval with 0 and pi left out.
On the middle page,
Yes.
you have a solid dot
This
at
is a
pi,
solid dot, yep.
so you don't, so
Well,
is it a bracket or?
that's a different question. Even though the graph is filled in there, the question that you're answering is where is the function defined?
Okay.
Does that make sense? The function does have a value at pi, but this question that we were asked is where does the limit exist? And if you were to include pi, put a square bracket around like the first one, say, then you've actually included pi as a place where the limit exists. So I think that's the difference in the question.
Okay.
But the thing is, the answer would have been the same if these would have been open circles. Or if the dots would have been filled in the opposite order. Both dots can never be filled in, right? Because then you wouldn't pass the vertical line test, you wouldn't be a function. But yeah, that's a mistake that actually occurred when I gave this question in the past, is that students felt like, oh my gosh, that dot's filled in, so I have to include it. You're not asked to find the domain and range, you're not asked to figure out where the function is defined, you're asked to figure out where is the limit non-existent. It's non-existent at those 2 points. The interval that leaves those 2 points out is this interval. Does that make sense?
So if both dots at 0 were filled in.
If both dots at 0 were filled in, it wouldn't be a function, right? The way that you would include 0 is what if I wouldn't have made it negative cosine? What if I would have left it as positive cosine? This blue part would have been flipped, right? But then would the limit have existed at 0? I'll just draw it in there so you can really see it. It would have looked like this in that case, right? So then would the limit have existed at 0? Yes, because as you go from both sides it matched up. And then you would have included 0. Does that make sense? So yeah, it doesn't matter which dot was filled in. What matters is did the limits match up at that particular value of x? I also made you review graphing piecewise functions. Mwahaha. I'm going to erase that purple part so the wrong part's gone, but my eraser just defaults to humongous. Okay. So there you go. So sketch a graph that meets the following conditions. So for these, it's just trying to see if you can dissect what's given. On the WebAssign questions, these become multiple choice, and it says pick which one actually meets these conditions. So as x goes to 3 plus, which means x goes to 3 from the right side, your y's get close to 5. So my axis doesn't have enough things. Let's call this 2, let's call that 4. Okay, we can relabel, and we'll call this by ones. 1, 2, 3, 4. 1, 2. You're totally allowed to make axes unequal as long as you label them. Okay, so as you go to 3, your y's get close to 5 from one side, and they get close to 1 from the other side. So I'm going to draw 2 open circles, one at 1 and one at 5. And I'm going to decide which one to fill in later, if any. The limit as x goes to -2 of f of x is 3. So near -2, we're getting close to 3. Make an open circle and decide what to do. The last 2 things tell us when we plug in 3, what do we actually get? So I have a filled in dot down there. So can I fill in either of my other 2 dots? Nope, because it wouldn't be a function anymore. And how about at -2? 2. So does the dot get filled in the right place? No. And that first dot I drew is supposed to be above that one, so I'll redo it. Okay. Other than that, your function can do whatever the heck it wants in the middle. So for condition 3, it says you have to get close to 3 on both sides. Your function has to come at 3 and come at 3. And it could do it by increasing or decreasing, doesn't matter, just has to get close to 3. It could do some wiggly craziness as long as eventually it gets close to that number. And you have to approach this dot and then approach that dot. That's one potential correct thing. You could also go on like, woo, woo, like that. I mean, it's the same, still fits the same properties, right?
It doesn't really matter how we draw the line.
Nope. No, because for that one, if I give it to you, I have to think. Like, I can't say, oh, it must look like this. It must just actually meet those properties. Yeah.
And you don't have to draw a line through the actual filled-in dots.
Yep, the filled-in dots, nope, the line won't go through the filled-in dots. And the reason that the line can't go through the filled-in dots is because of these limiting things. Like saying the limit has to get close to 3 at -2 means that your function has to get close to 3 at -2. So it can't possibly go down and get to that dot. Does that make sense? Exactly. And so this one says, well, as you go at 3 from the left, you have to get close to 1. So your function has to eventually go near to 1 near that value on that one side. So what I would think the best way to do these questions is sketch something and then see if, go back and recheck your conditions, like are they met? If you go at 3 from the right, do your y's get close to 5? Yes, they do. If you go at 3 from the left, do you get close to 1? Yes. If you go to -2, do your y's get close to 3? Yes, they do. And are these last two conditions met? Well, those are the easy ones. Okay. We also use limits. So technically, limits exist must actually equal numbers. But sometimes it's useful to say that the limit is equal to infinity because it describes what happens at that point. Like, does the function get really, really big or really, really negative? So have you seen this function's picture? 1 over x squared looks like this. Okay. And so as the x's get close to 0, do those get close to a certain kind of infinity? Positive infinity. And so some books will say a limit equaling infinity is non-existent, but in this book at least they want you to say if the limit is infinite, tell them what kind of infinity. It's non-existent in a specific manner.
So because there's no jumping in infinity, they agree.
Yep, I'm going to change example 8 slightly to give one that does not exist. So for example 8, let's change it to positive 1 over x instead of 1 over x squared, okay? So 1 over x, we graphed this earlier, looks something like this, right? So as x goes to 0, and that going to 0 implies from both sides, does this limit go to one particular kind of infinity? No. So this one you can just say does not exist, like as not even as a certain type of infinite limit.
But if you specified it positive or negative.
If I specified plus or minus in that limit, then you could say exactly. Yep. Without the specification, it means both sides, like by default. Exactly. So that, I think this, so those lines are called vertical asymptotes, and you have a vertical asymptote if the limit as you go to that number from either both sides or the left or right side is infinite. So as you approach a specific number, what happens to your y? I think the next thing we have is a picture, right? So find these limits, so state them as infinities. Yes?
Can you have an asymptote approaching from one side and a finite number approaching from the other?
Yeah, you could. So you could have a function that looked like this, and there was the asymptote, and then it was, say, piecewise, and you defined it there and like did something like that. So yeah, that's a weird function, but it is totally possible. Yep. Okay, great. So look at this picture. As x goes to 2, Does r of x settle on a specific kind of infinity at 2? Negative infinity, exactly. How about as x goes to 5? Positive infinity. How about as you go to -3 from the left? Negative infinity. Because -3 from the left means you're on the left side of -3.
Also, if it were to just say, 2, 3 without like the negative.
If it said -3 without a negative or positive, then you would say doesn't exist. Exactly. How about -3 from the right? Positive infinity. Okay, and then the equations of the vertical asymptotes. So what are they? Yep. X equals -3, 2, and 5, right? That's just me being lazy, but that's all of them.
And x of 2 and x of 5 are the only two limits.
Say that again?
Is the only two, are the only two that actually have limits though, right?
Yes, but the fact that the limit does not exist at -3 doesn't mean there isn't a vertical asymptote there. Does that make sense?
Yeah.
So this question is just asking where are there vertical asymptotes, and the point that they're making in this question is that even though the limit doesn't exist, there still is a vertical asymptote. To have a vertical asymptote, all you need is the limit from one of the sides to be infinite. So that's like this picture has that property. Natural log of x also has that property, right? Because you now all have the ln x picture memorized. Yeah, looks like that, right? As you go to 0 from the right, ln x goes to -infinity, right?
I did the other one.
You did e to the x, didn't you? Oh.
Well, I just memorized that one. When I saw the other graph.
Okay, so one way you could get infinite limits is by looking at a picture. Another way is using clever reasoning. I love this clever reasoning thing, it's so much fun. Okay, so we're gonna figure out where does the numerator go, where does the denominator go, and that will tell us what kind of infinity. You could use graphing to check your answers, like if you're at home working on your homework, okay? So, as x goes to 3 plus, where does 2x approach? Not a trick question. X is going to 3, 2x is getting close to 6, okay? So your numerator, I don't know what I was trying to write there. Your numerator approaches 6, okay? So there's the numerator. Now the denominator. X goes to 3 plus, we're told that, right?
So 3 plus minus 3 is 0 plus, which is something that's really, really small, close to 0.
Exactly. That means x is bigger than 3. Do you guys buy that? If you're on the right side of 3, you're a little bit bigger than 3, right? So what's true about x minus 3? It's bigger than 0. Does that make sense? Which means x minus 3 goes to 0 plus. So what you have is you have 6 divided by 0 plus, as in 6 divided by a little bitty positive number. If you do 6 divided by a little bitty positive number, what does that make? 6 divided by 1,000th, 6 divided by a millionth. Makes it big and positive. So this will be infinity.
You're still on the other side of the house.
Yep. Yes. Okay. So what you need to do is figure out the sign of the numerator and the sign of the denominator. Does that make sense? What if this had come out to be -6? You have -6 divided by a small positive number, which still makes some kind of infinity, right? But because this had been negative, it would make negative infinity. And I'll have an example of that too, okay? Okay, same thing, but 3 minus, okay? So your numerator, still goes to 6. Because you're still getting close to 3. 2 times 3 is 6. And your denominator, as x goes to 3 minus, x is a little bit less than 3, right? Now you're picking, think about what numbers you'd pick. You'd pick 2.9, 2.99, 2.9999999, right? And if you do 2 point something minus 3, you're going to get a negative answer, right? In other words, x minus 3 is less than 0. So x minus 3 goes to 0, but it's a little bitty negative number. So if you do 6 divided by a little bitty number that's negative, what's that going to make? A large negative number, in other words, negative infinity. So if you were to graph this picture, you should see something that at 3 looks like this-ish. And that picture would confirm what you've done by guessing. Don't use that until you've actually run through the reasoning. Does that make sense? Okay. Ooh, cosecant. Okay, you could look back at the picture of cosecant that we made before, right? Or if you forgot that, you could remember that cosecant is 1 over which function? Sine. To graph cosecant, I have to graph sine anyway. It's just how I work. So I mean, like, I'm just going to graph sine. Okay. So 2 pi. I feel like I've graphed sine like 20 times already this semester. So man, you better know how to graph sine. Okay. So the problem here is that sine of pi is 0, right? So as x goes to pi from the left, sine of x goes to what kind of 0? Does it go to a positive 0 or a negative 0? You can tell that from the picture, actually. You're going at pi from the left. You're approaching pi from this side, right? It's going to positive 0.
It's just because it's on the upside.
It's because of the left side, yep. If I would have said pi plus, you would be approaching pi from this side and be going to 0, but it'd be a little bit negative, right? So this will be 1 divided by some small positive number, right? What's that going to make? What positive or negative would be? Positive infinity, right? And you could confirm that by looking at what cosecant's graph is. Remember, cosecant had an asymptote there, and then it did this kind of business, right? As you go at pi from the left, cosecant goes to infinity, right? As you go at pi from the right, cosecant goes to negative infinity. So your job, the numerator, the difference with these from the previous ones is the numerator is a fixed specific number, and the denominator is some kind of 0. Do you know what I mean by that? A positive or negative 0. Okay. ln of x squared minus 9. Okay, so here's the thing to remember. Y equals ln of x. Looks like this. As x goes to 0 plus ln x approaches what? So look at the picture of just regular ln. We're going to go back to this one for a second. As x goes to 0 from the right, what happens to ln? It goes to negative infinity. Okay? So for this thing, if x goes to 3 plus, so x goes to 3 plus, that means x is bigger than 3. And assuming we have positive numbers, then x squared is bigger than 9, right? and x squared minus 9 is bigger than 0. So x squared minus 9 is going to 0, and it's a little bit positive. What happens if you take the natural log of a little positive number? It goes crashing to negative infinity. If I'd asked for the limit as x goes to 3 minus of the same expression, this wouldn't exist. And that's because if your if your number you plug in is less than 3, this expression in here is negative. Does that make sense? If this x is like 2.9, 2.9 squared is less than 9, right? And that's going to make a negative number. You can't log negative numbers, right? So that ln function, it's asymptote only defined from one side, not both, because the function doesn't exist for values on the other side of it. But the point is that ln also has an asymptote, and ln of 0 plus is equal to minus infinity. I'm pretty sure some calculators, if you plug in ln of 0, they give you minus infinity. So.
It says undefined.
Yours is undefined? Okay. But you probably could ask it to find the limit. I think I put a couple more questions on there, didn't I?
Yes.
But we're almost done. Oh, find the vertical asymptotes. This is not so hard. So vertical asymptotes occur when you have a denominator that's 0, but the factor doesn't cancel out. So, and that's true with rational functions. So look at this function. Does x squared plus 1 factor?
No.
Nope. That's a prime polynomial. Can you factor 3x minus 2x squared?
Yes.
Take out an x. 3 minus 2x. So vertical asymptotes will occur where that denominator is 0. So when is the denominator 0? And at x equals 3/2. You find that 3/2 by taking 3 minus 2x, setting it equal to 0. So 3 equals 2x. X is 3/2. So those are your two vertical asymptotes. Some Algebra 2 classes teach that. Like I know mine did, I know Benson's did. Other people I don't know. And you look for the places the denominator is 0 after you canceled out any common factors. So part B has some common factors that will actually cancel out. So can you factor the numerator of part B slightly?
Yes.
Take out a 2. And then x to the 4th minus 1 is a difference of squares. So that factors into x squared plus 1, x squared minus 1. X squared plus 1, x plus 1, x minus 1. So I'm going to stop and pause for a sec. And after today, I promise I'll stop going over. So do you buy that factorization pattern? Okay. I made this tricky on purpose. Does it appear that anything factors right now? No. But the 1 minus x and the x minus 1 look awfully similar. Does that make sense? And here's the tricky thing you can do. You can take out a negative. If you take out a negative, what does it make that expression into? X minus 1. And now, do those factors cancel? Yeah, they do. And so that is negative 2 over x squared plus 1, x plus 1, so long as x isn't equal to 1. So where does this thing have a vertical asymptote? At negative 1. Is the x squared plus 1 ever 0 for real numbers? Only imaginaries. at x equals +1, the graph has a hole. I don't know if you guys have seen stuff like that before, like I made my pre-calculus students do that. Have you seen holes in asymptotes before? I think I'll have, tomorrow I had planned to do like a little bit like a lesson and plus having you work together and work some problems in class, so I'll go over a little bit about holes and asymptotes tomorrow as well.
Seems like an asymptote is a huge one.
Yeah, a hole is, yeah, so we'll do that.